네, 뭐, 한 분이라도 재밌으셨다니 다행이네요. 네, 사실 뭐, 인터넷에서 찾아보시면, 사실 파이토치만 들어가도 바로 그 DC겐 튜토리얼이 있어가지고, 어떻게 보면 뭐, 거저먹기가 아니었나 생각합니다. Alright, I think we can get started. 시작하기 전에 네이버 분들은 혹시 채팅창에다가 자신의 성함을 좀 써주실 수 있으실까요? 출석을 좀 회사 측에서 부탁을 하셔가지고, 네, 채팅창에다가 자기 성함을 좀 써주세요. 감사합니다. 배치 사이즈는 작을수록 학습에 좋은 걸까요? 배치 사이즈는 데이터셋의 사이즈에 따라 다릅니다. 데이터셋이 엄청 크면은 배치 사이즈를 크게 하시는 게 좋고, 데이터셋이 작으면은 배치 사이즈를 작게 하는 게 좋고, 그게 그냥 룰 오브 썸인 거로 생각하시면 될 것 같습니다. GPT-3 같은 경우는 배치 사이즈가 100만이 넘어갈걸요? 제가 제대로 기억하고 있다면. 그러니까 전체 데이터셋 사이즈가, 배치 사이즈가 100만 토큰, 이랬을 거예요. 네, 이원주님 좋은 질문이신데, 네. 기본적으로, 네, 노가다라고 생각하시면 됩니다. 하시다 보면은 경험이 쌓이고, 그러면 이제, 직관이 생기거든요. 어떻게 해야지 좀 잘 될 것 같다. 네, 그래서, 그렇게 하시는 거고, 그 다음에 그게 싫어서 이제 튜닝을 자동으로 해주는 게 하이퍼 파라미터 옵티마이제이션이라고 그래서, 그런 패키지들이 또 있어요. 그러니까 이제 하이퍼 파라미터를 자동으로 해주는 알고리즘들이 있는데, 그런 걸 쓰셔도 됩니다. 그래서 베이지언 옵티마이제이션이라든지 네, 그런 것들이 있는데. 근데 그렇게 막 아주 탁월하게 잘하진 않아요, 사실. 네, 이폭 50에서 D로스가 1이고 G로스가 0이라면 그건 제너레이터가 이기고 있다는 건데. 보통 그런 경우는 흔치 않은데. 네. 그런 식으로 극단적인 값이 나오면은, 네, 그냥 다시 시작하는 게 좋을 것 같습니다. 아니면 중간 이폭을 꼭 50을 쓸 필요 없고, 이폭을 50까지 돌리셨으면 중간 이폭들이 있을 테니까, 이폭 25짜리를 쓰시든가, 그렇게 하시면 될 것 같습니다. 그렇죠. D로스가 0에 수렴하는 경우가 더 많죠. 아무래도 디스크리미네이터가 이 수행하는 작업이 더 쉽기 때문에, 가짜인지 진짜인지 판별하는 게 이미지를 만드는 것보다 쉽잖아요. 그러니까 보통은 D로스가 훨씬 낮아지는 경우가 많습니다. 네, 문명지훈님, 네, 되게 그렇다고 보시면 됩니다. 근데 그렇다고 D로스가 0이라 그래서 G가 아무것도 못 배우고 있느냐, 꼭 그런 건 아니거든요. 근데, 일반적으로 둘이 균형을 이루는 게 좋은데, 퍼펙트 균형을 이루는 경우는 별로 없습니다. 보통은 이제 디스크리미터가 더 쉬운 일을 하기 때문에 D의 로스가 더 낫습니다. 네, 시작하겠습니다, 그러면. 네. Alright, we'll get started. So today, I guess the title page is a bit incorrect. So it's not natural language processing. It's word-to-vec and subword encoding. word-to-vec and so this we'll talk about word-to-vec. We're just gonna skim through it because we will cover BERT separately. So contextualized word embedding. That includes BERT and Elmo and all those BERT variants, like Albert, Roberta, whatever. Those are contextual word embeddings. We'll deal with them later, so we'll just skim through it. Subword encoding is what you usually hear these days, including BPE, byte pair encoding, word piece, or sentence piece, those kind of stuff. So yeah, today's it's gonna be relatively easier than previous chapters. So we'll just we'll go through it step by step. So yeah, embedding. So mostly we're gonna talk about word embedding, but we'll just spend a page or two talking about document embedding. But it's just a straight up extension of word embedding. So yeah, no worries. The reason that we are going through word embedding before we go through RNN and sequence to sequence, transformer, all that is because word embedding is like the foundation of modern deep learning based NLP. So everything is treated as a token. Like unlike image processing or computer vision, where you usually use CNN, there's a you don't have a lot of like tokens or embeddings because you usually embed the entire image into a representation vector. But here in NLP, there's a unit of how should I say this? Like a sentence is a composition of words, or document is a composition of words. Like words are like the fundamental unit of NLP, and each word is treated as a vector, as an embedding, as a vector, as a representation vector, or distributed representation. Like they are all the same thing. So word embedding is word vector, word representation vector. Like they're all the same thing. So. Yeah, as I said, so word is like the foundation, like it's not these days because there's Subword encoding, but back in like 2014, 2015, back in the day, people usually treated words as the atom of NLP. So yeah, that's why we first go through word embedding to get to understand the concept how like everything is just turned into a vector. And they do and each vector, word embedding or word vector, they capture some meaning. It's not just they're like one hot encoding. They actually seemingly capture semantic meaning. So we'll go through that. So as I said, express word as a vector. So hopefully a good word embedding, they will capture some meaning, as I said, some semantic meaning. So for example, cat and kitty are similar words, so they should have similar vector representation. For example, if cat is, I don't know, if cat is represented as a three-dimensional vector, like 0, 1, 0, 0, then kitty should be at least 0.500, something like this. There should be some similarity between the two because they are actually similar words. But hamburger is not similar with either cat or kitty. So they have different vector representation. They should have different vector representation. So hamburger, while cat and kitty should have similar vector contents or similar vector values, hamburger should not. So, and a vector is actually just it's an arrow. You all remember what vectors are, right? So vectors and scalars, and vectors is like if this is a x1, x2 two-dimensional space, then a vector can be like here. Anything is a vector, anything, right? And specifically, cat vector and kitty vector should be similar in their values. So maybe this could be cat and this could be kitty. So the distance between the two, the distance being distance between cat and kitty, which is this here, or the arrow could go the other way because it's a distance. So it could be like L2 distance, or it could be cosine similarity. It's some measure that evaluates how close they are, the kitty and cat. So in that, and while that hamburger should be, maybe this could be hamburger. I mean, not necessarily the opposite direction, but it should be like as far away as possible. So hamburger. So in that case, the distance between cat and kitty, and distance between cat and hamburger. So cat and hamburger, distance would be really, really large, right? So that's somehow capturing the semantic meaning of words. The distance kind of represents how close the two words are and how how similar or dissimilar two words are. The token is one of the methods. Actually, the words and tokens are about the same thing. So token and words, they mean about the same thing in NLP. Not necessarily. I mean, token is what you actually input into your encoder. It could be your transformer, it could be a 1D CNN, it could be RNN, but something that goes into a sequence encoder, you call that usually a token. And back in the day, 2014, 2015, 2016 even, words were the tokens because you put words into RNNs or whatever, or transformer. But these days, modern days, like BERT, like you don't put words into the encoder, you put subwords like word piece or byte pair encoding. So those become the tokens. So these days, tokens are no longer words, they're subwords. Right, moving on. So before like all the deep learning era, it was usually treated in a very straightforward, maybe naive or like logical way. Everything was encoded as a one-hot encoding. So one-hot encoding, meaning that you have a vector of zeros and only one element is non-zero, meaning that only one element is one and all the others are zeros. So it's a categorical variable, something like a softmax label. So for example, if you're encoding a variable, encoding a blood type, like it's either A, B, or AB, or O, and if you encode it in a one-hot encoding, then it's simply just A being 1000, B being 10100, AB being 0010, like this. So this is pretty straightforward. It's very understandable. It's very understandable, also meaning it's very interpretable. You just look at this number and you can readily know that it is A, and you can readily see this is B, and AB and O. But unfortunately, this doesn't capture any meaning between different blood types. Like, for example, you would assume that A and AB should be somewhat similar compared to A and O. Maybe I'm just making them up, but but this doesn't have any meaning because everything is exactly the same distance away from each other. Like AB, the difference between AB or the distance between AB is the same as difference between A and AB, or A and O for that matter. The distance or L2 distance is always is a square root of 2, something like that. So it doesn't capture any meaning or any any subtle nuance of words. So anyway, but that's the start though. You first encode everything, all the words, all the tokens, or everything in your vocabulary as one-hot encoding, and then somehow you transform them into a word embedding. So we'll get to that later. Yeah, so as I said, so each word can be represented as a one-hot encoding, which each word takes up its respective dimensions. So respective dimension meaning like if there are 3 words in your dictionary, if there are 3 words, then those words are let's say this is dog, this is cat, and this is horse. Then if you use one-hot encoding, that means you either have 100, meaning that 100 being dog, or 010 being cat, or 001 being horse, and that's it. So each word takes up its own dimension. So that's quite a bit of waste of space though, right? But anyway, that's the basic approach, just one-hot encoding. So horse and zebra could be, like horse could be responsible for the 5th dimension. Zebra could be responsible for 11, 12th dimension or whatever. But at least you can distinguish between the two. Using a one-hot encoding, you can easily distinguish between different words, and they are interpretable, as I said. So there's like, it's not just all bad. It's pretty, intuitive. But the inner product similarity between the two. So similarity could be measured in a lot of ways. It could be like, as I said, it could be distance, it could be cosine similarity or whatever. But usually a lot of people use inner product similarity. So you just given two word vectors, you can just simply do an inner product between the two. And then if they're close to each other, then if they're similar to each other, like their values are similar, then the value of inner product will be high. But if they are completely orthogonal, then the value of inner product will be 0, right? So in this case, horse and zebra, the inner product between the two would be 0 because they are orthogonal. Basically, they're just bases of a high dimensional space, right? So, I mean, like there's one here and there's one here, and all the others are 0 here. So if you do inner product between the two, it's just 0. 이해선 17개? I'm not sure if this is just 17, 1, 2, 3, 4, 5, 10. But yeah, okay, so this is 17-dimensional vector. So we're assuming that there are only 17 words in your vocabulary or in your dictionary. But it's just an example. As I said, so inner product similarity is 0, not just between a horse and a zebra, but between any pair of words, because it's one-hot encoding. So if you take any 2 words in your vocabulary and apply inner product between the two, then it is always 0. So nothing is similar or dissimilar. In the same manner, Euclidean distance is always square root of 2. So if you just, like horse minus zebra, 2, not 2, I'm sorry. This is square root of 2, but it's the same for all pair of words. It's in the same manner. So so if you think about this, like all Euclidean distance between any 2 words is square root of 2. Inner product similarity between any 2 words is 0. That means it's not a very good representation method of words, because words have similarity and dissimilarity, like at least meaning-wise, or at least like syntax-wise, like pretty, prettier, prettiest. Those 3 words should have some similarity, but if you use one-hot encoding, then all meaning is lost. So while intuitive and interpretable, one-hot encoding is not a very good way to represent words. Right, yeah, as I said, horse and zebra should be semantically similar to the horse and desk. Same stuff, right? So it's the same manner. It's you can extend this logic beyond just words. Like you can apply the same logic to documents or sentences or whatever. If anything that has words as a unit of expression, then you can apply the same logic. So, for example, there are 2 documents, document 1 and document 2 here, document 1 and document 2. One is John likes movies, Mary likes Sue. Another document says John also likes football. Now, you can kind of expect that they are, like if there are document number 3, so doc number 3 being Trump won the election, something like that. This third document has nothing to do with document 1 and document 2. While document 1 and document 2, they seemingly they're way more closer to each other than document 3. So doc 3 should be like doc 3. It should be like all 0, 0, 0, 0, 0. I mean, there should be more words here, like more vocabulary, but at least this should be all 0. So, and if you represent document as document 1, document 2, document 3 as a one-hot vector, that's a bad idea. So what people usually do is they use something called term document matrix. And the term document matrix is there's a term axis here. So this is all terms, like John likes movies, also football, married to Trump, whatever. Like this axis will be representative of words, and this axis is representative of documents. So this is a term document matrix. In this case, if you represent document as a count vector, like John occurred once in the document, likes occurred twice, likes occurred twice in the document, something like this, like a count vector, then at least this is a better representation than just representing document as one hot encoding again, right? And then if you do inner product between document 1 and document 2, it should be higher than the inner product between document 1 and document 3. So you can like extend this logic the same way. Right, so yeah. We'll just skip this. This is old school stuff. It's just, try to. There are different ways to represent words. Something using like matrix vectorization or probabilistic topping model like LDA or hierarchical Dirichlet process. All those graphical model stuff. We'll just skip that. All right, so word embedding methods. There are mainly two well-known methods. Like this is like the old school methods. These days, nobody really uses this anymore, at least in NLP. They have all moved on to BERT and all those variants. So word2vec and glove. We'll take a look at them today, and then we'll move on to doc2vec, which is a way to represent documents, not just words, but it's just a straight up extension of word2vec. So it goes like this. So distributed vector. So some people back like in 2013, 2014, some people called word vector as distributed representation, distributed vector representation. That's because it's not a one hot vector. It's the values are distributed across all dimensions. It's like like cat could be 1.0, negative 1.5, maybe 0.3. This is cat, and a kitty could be like 0.9, negative 0.4, positive 0.6. This could be kitty. So it's no longer like each dimension having either 0 or 1. Now continuous values take up space everywhere. So it's a distributed vector representation. And and if you have a representation like this, then you can use Euclidean distance, inner product, or cosine similarity between two words to calculate the semantic similarity. So you can readily see that cat and kitty, their distance should be smaller or shorter, and their inner product between cat and kitty should be higher compared to just one hot encoding. And the essence or maybe the philosophy of word2vec is that the semantic meaning of words can be captured by looking at its neighbors. But before that, so the meaning of using distributed representation or continuous vector compared to one hot encoding is that you can see it's kind of a cute depiction. Here, the word cat is a clear, it's not like compared to this one's blurry, and this is pretty clear, crystal clear. So this one's blurry. And the reason that this figure actually emphasizes the blurriness of a distributed representation is because it's no longer like, for example, 0. If a cat was 0, 0, 0, 1, 0, and if you perturb this. If you change this to like 1, 0, 0, no, actually this 0, 0, 1, 0, 0. If you change this to here, then this is a completely different meaning. This was cat. Maybe this was a dog. Like just by changing a small value, you are actually completely changing the semantic meaning of a word. But here, if you change this to 34.3, 94.4, 46.5, something like this, then this is still very, very similar to cat, So there's no longer a fixed cat vector. So that is why this is blurry. So if as long as you're using a continuous vector to represent words, then there's no like the vector for a cat and the vector for dogs. Like it's just a different flavors of dog or different like subtle, different spectrum of dogs. Right, and So yeah, anyway, so the core essence of Word2Vec is that the words in similar context will have similar meaning. So the context meaning it's just the neighbors. So, for example, the context could be a context of, in this particular example, this sentence, the context of cat is just its neighbors, the and per. In this example, here in the second sentence, the context is the and hunts and mice. So it's just where the neighbor of the given word. And as I said, words in similar contexts will have similar meanings. So the core philosophy is this: there's some hidden relationship between the and cat. So let me just erase all this. There's some hidden relation between the and cat and purrs because they're in the same context. Again, there's some hidden relationship between cat and hunts, cat and mice, and cat and the because they're all in the same context. And the Word2Vec is trying to capture that relationship. There was a question. Let's see. 전 같은 월드는 원합 같은 방법을 이미 알고 있는 것인가요? 텀 도큐먼트 매트릭스 말씀하시는 것 같은데 맞습니다. 그렇게 보시면 됩니다. Right. So history of Word2Vec, I guess it's not a history of Word2Vec, but a history of word embedding, actually. So Word2Vec is not the first method to represent words as a distributed representation or a continuous value, continuous vectors. Even before that, back in like a long time ago, like Yoshua Bengio, of course, the father of the deep learning, he came up with some neural network, very simple neural network to represent words as a vector, not just one-hot encoding, but some distributed representation vector. And then back in 2008, this was a seminal paper that empirically showed that even without like any domain knowledge, like like morphological, semantic, like all those like very old school NLP stuff, even without that, just plugging in, just simply using neural network could show similar performance compared to like very engineered NLP models. But back in 2008, the neural network based approach couldn't outperform the old school NLP approach because of all the like hardware limitation and the size of data set and just the algorithms weren't as sophisticated as now. So, but it was a very seminal paper in retrospect. And in that paper, they also kind of used word embeddings, but they didn't really emphasize on that aspect. And then now 2013, 2014, Word2Vec came along and then it just blew everybody's mind. So why did it blow everybody's mind is, as I said, the core philosophy is very simple. It's just that words in similar contexts will have similar meaning. And that's all there is to this model. It's just trying to capture that similarity between words in the same context. But the reason that it just, surprised everybody is because based on that very simple approach or very simple philosophy, the product or the result were surprisingly well capturing the semantic meaning of words. And the example of Word2Vec capturing semantic meaning is here. So they were very Word2Vec vectors. The Word2Vec results were really good at linear operation between words so simple linear operation between words. They were surprisingly well capturing semantic meaning between words. So, for example, everything is a vector, as I said, in a high dimensional space. So, for now, like man and woman, uncle, aunt, queen, king, they're not represented as one hot vector. They are represented as some n-dimensional vector. Like it could be 10 dimensional, it could be 20 dimensional, it could be 500 dimensional. That's all up to you. It's a hyperparameter, but each word is represented as a vector, fixed size vector, and that means you can assume that there's a origin somewhere. Like let's just assume that this is a two-dimensional space, and man vector is here, king vector is here, uncle vector is here, woman vector is here, aunt vector is here, queen vector is here, something like this. So, and surprisingly, the distance or the difference between two vectors were capturing the hidden relationship between them. So I'm just going to erase all this now. Difference between man and woman. So there's a man vector, woman vector. Difference between the two is this one, because this is a vector, this is a vector. So difference between the two is the same as the difference between uncle and aunt, and king and queen. So the difference is, what is the difference? What does this mean? What does this relationship represent? It's the man and woman relationship. It's the male and female relationship, and that essence is captured in all like proper pairs of words, like woman minus man, aunt minus uncle, queen minus king. It's the same content, same vector all over. So that means what you can do is queen minus king. As I said, queen minus king and woman minus man, they have the same relationship. They have the same content. And that means what you can do is you can just shift like a lot of stuff. So what you can do is, let's say that, yeah. So if you take this term to this side, what happens is it's king minus man plus woman is what? Semantically, it should be queen, and this works. So if this is true, then of course, obviously this is true, right? It's just simple manipulation. So king minus man plus woman becomes queen, which is it's so reasonable. And word to vec vectors could do this kind of operation. It was very good at this operation, and this was done with no intention of injecting semantic meaning into the words, because as I said, word to vec, all it does is just try to learn a word vector that maximizes the similarity between two words in the same context. Similar context, similar meaning. That means similar vectors for words in the same context, and that's it. That's all word to vec does. And by doing so, you were able to do this kind of linear operation. So that's why everybody was just blown their mind, and it was just so mind blowing that the simple approach as word to vec could capture semantic meaning, and all previous efforts, semantics was such a important concept or important element in old school NLP, and a lot of researchers spent a lot of time trying to capture the semantic of words, or semantic of sentences, or semantic of documents, and a lot of super smart people came up with very elaborate models and such and such and such. But this word to vec showed that none of those were really kind of necessary, because just by looking at the context, that's all you needed to understand, to learn the semantics. I mean, obviously this is exaggeration. This is a stretch, but that's kind of like what people felt like by looking at word to vec back in 2014. All right, some couple questions. 개출형 단어가 벡터화. As I said, 그러니까 1대1 대응하지 않습니다. 제가 말했죠. cat 벡터라는 건 더 이상 존재하지 않는다고. cat의 여러 플레이버가 존재할 뿐이지. 그래서 이게 blurry한 겁니다. 그리고 단어와 벡터가 1대1 대응이라면 주변과 관계에서 단어. 네, 단어와 벡터 1대1 대응이 아니에요, 더 이상. 네. Alright, moving on. So this is the actual example of word2vec. So if when you do word2vec, you typically back in the day, typically people just use like 100-dimensional vectors to represent words, but you still want to draw them. You want to visualize them on 2D plane. So what you do is you use t-SNE. So everybody should remember t-SNE, right? So you can either use PC or t-SNE, but some additional step to downsize your 100-dimensional word vector into 2-dimensional vector so that you can draw a plot like this. And this is the actual example. I actually took it from the paper, the word2vec paper. And you can see how nicely the word vectors capture the semantic meaning or the relationship between words. So aunt and uncle, niece and nephew, sister and brother, is all like male-female relationship. Heiress, heir, madam, sir, woman, man, countess, countess, earl, duchess, duke, whatever, like king and queen. It's all vector like this. So this vector in this model or in this word2vec implementation captures male-female relationship. And obviously, interestingly, you can tilt this slightly like this or like this, and it will still capture male-female relationship. Again, just as cats or dogs can have different spectrum or different flavors of cats and dogs, relationships also can have different spectrum. Like, you can see that sister and brother are a straight up vertical vector, but heiress and heir is a bit skewed. So maybe they're capturing a bit of a slightly different semantic, which is hard to interpret though. Again, what is this? This is a company and its CEO. So Exxon's CEO is Tillerson. Walmart's CEO is Macmillan. Citigroup CEO is Corbett. IBM CEO is Rometty, and such and such. So again, like subtle difference, like this here, and a straight up horizontal vector. There's a subtle difference between the two. 마이너스가 실제 구현할 때도 벡터가, 네, 맞습니다. 실제로 마이너스 연산이. 지금 이게 다 마이너스 연산, 디퍼런스잖아요. 디퍼런스니까. 그러니까 여기에 이런 벡터가 하나 있고, 캐터필러 벡터가 있고, 오버헬만이라는 벡터가 있고, 그 사이에 그냥 빼기를 해주는 겁니다. 근데 그 빼기가 다른 여러 페어에서 똑같이 나타난다는 거예요. 그러니까 이 의미적으로 똑같은 페어가 있으면 그 사이에 빼기를 한 결과가 다 똑같다는 겁니다. 지금. 아까 보셨듯이 시스터 앤 브라더에서도 빼기를 하면 이렇게 되고, 우먼 앤 맨 빼기를 하면 이렇게 되고, 뭐 킹하고 퀸 빼기에도 이렇게 되고, 그러니까 이제 다 똑같다는 겁니다. 그 빼기가 실제로 워드의 어떤 그 시민텍 의미를 이제 잡아내고 있다는 겁니다. 네, 요거 이제 집 코드는 이제 이건 I'm sorry. So this is city and its zip code. So, and again, it works pretty well. Interesting, very, very interesting. This is, again, a bit more interesting stuff. So this is comparative and superlative. So like pretty, prettier, prettiest. So they're slower, slowest, shorter, shortest, strong, stronger, strongest. And it's the same across all like triples. It's always going a bit like this relationship captures, or this vector captures the relationship between a word and its comparative word. And this one captures a word's comparative and superlative form. And it works well in all languages, actually. So there's a website which applied word2vec on Korean, like bunch of Korean documents. And now 한국 빼기 서울 더하기 도쿄. 요거는 뭐냐? 이건 당연히 일본이겠죠. 네, 일본이죠, 일본. So it works in all languages. I guess in all word-based languages, because this is word embedding. So if if there's some language that doesn't have words, I guess, yeah, I don't think it makes sense. Any language should have words. So, right. Anyway, yeah, and yeah, this is a bit more extensive example. So very interesting, Barack Obama minus USA plus Russia is Putin, Vladimir Putin. Some very interesting stuff. Yeah, here I find it very interesting. Like computer minus machine plus human is operating system. Interesting. Game plus study is programming. 소녀시대, girls' generation, minus girls, plus 아줌마, which is an older woman, is IU. This is pretty, insulting to IU, I would say, because they're like the same age, right? 소녀시대 and IU, they're like the same age, if I'm correct. Mathematics minus proof is management. I'm not sure if that makes sense. Yeah, this was also fun. IU minus song plus acting is 송중기. I'm not sure what's the similarity between IU and 송중기. They're not even the same gender, and I'm not sure if they're of the same age. Yeah, I should say IU 빼기 노래 더하기 연기 is probably 이지은, because she was in a lot of dramas and movies, right? Yeah, this was also fun. Like 최연석 셰프 minus 허세 plus 셰프 is 이연복. So 이연복 is like the drier version of 최연석. Yeah. Some people couldn't agree on a lot of stuff here, but that's what word2vec captures. So, yeah, this one is pretty insulting to British food. Fast food, negative changeum. What's changeum? It's like franchise. It's British food or English food. So English food is just fast food without franchise. I hope there's no English or British students in this class. Right, moving on. So yeah, anyway, so 오른쪽에, so this is different. So this is one implementation of word2vec. This is another implementation of word2vec. It's just based on what documents or what corpus that you train your word2vec on, the result will be different, obviously. I would say this one is a bit more interesting than this one. But there's no wrong and right. It's just different realization of word2vec. Exactly, it's capturing biases within the data set. So if two word2vec captures the same semantic, like here or here, or here, it means that there's less bias. But things like this or things like this, then it means there's bias involved. Does word2vec separate 최연석 셰프 and 최연석 and 셰프? Yeah, that depends on how you tokenize your documents. This particular example happened to tokenize 최연석 셰프 as a single word, but that doesn't need to be. There were some questions. 단어 개수가 매우 많아지면 벡터 인베딩을 한다고 해도 커패시티가 부족해서 담아내지 못할 것 같은데 트레이닝한 단어 개수를 가지고 인베딩을 아주 정확합니다, 이재영님. 네. 그래서 뭐 단어가 예를 들어서 10만 단어쯤 된다. 그럼 한 뭐 넉넉하게 한 천 디멘셔널 벡터를 쓰셔야 되고, 뭐 단어가 뭐 10,000개밖에 안 된다. 그럼 이제 뭐 한 100 디멘셔널만 써도 되셨는데, 요즘은 이제 그런 거를 다 뛰어넘어서 이제 그 서브워드나 바이트 페어 인코딩을 하기 때문에 이제 좀 시대가 달라졌습니다. 옛날에는 이제 단어의 개수를 얼마나 이제 다양한 단어를 써야 되냐. 한 번만 등장한 단어도 써야 되냐. 아니면 적어도 10번 등장한 단어를 포함해야 되냐. 이 사전에. 그런 것들이 이제 좀 하이퍼 파라미터였는데 요즘 더 이상 그렇지 않습니다. 명철님, 한 단어에서 여러 릴레이션 그 복잡도 어떻게 유지하면서 설계한 건가요? 그거는, 네. 그러니까 릴레이션십 자체도 이미 멀티디멘셔널, 뭐 100디멘셔널짜리 벡터 뭐 이렇기 때문에 당연히 여러 릴레이션십이 녹아 있습니다. 그 100디멘션 안에. 그러니까 이제 그걸 빼기를 맨 빼기 우먼 할 때는 이제 메일 피메일 릴레이션십이 잡히지만 뭐 맨 빼기 보이 하면 또 다른 릴레이션십이 잡히겠죠. 뭐 이렇게 연령에 관한 뭐 이렇게 잡히겠죠. 마치 맨 빼기 보이랑 우먼 빼기 걸이 비슷해지겠죠. 그때는. 그럼 이제 그때의 빼기에서 나오는 벡터는 메일 피메일 릴레이션십이 아니라 뭐 나이 릴레이션십이나 어덜트 차일드 릴레이션십이 나올 겁니다. Alright, moving on. So the exact algorithm is, well, everything is just basically based on conditional distribution or conditional probability. So a word given its context. So the context becomes the condition and the word becomes your word. So given a context, you can calculate the probability of your word occurring. So like you shall know, this is a very old thing. You shall know a word by the company it keeps. So the definition or the identity of a word is determined by its context, which is a very strong claim though, but still it kind of works. So given a cat, given a context cat, what is the likelihood or what is the probability that you're going to see meow in your sentence? Or given a cat, what is the probability of seeing potato, seeing a parrot, seeing baguette, seeing flea, seeing pet? So obviously, depending on your context, seeing the word probability differs. So obviously, cat and meow has a lot of like similarity, or not similarity, but a lot. It has a hidden relationship. So given cat, a meow should have a higher probability than like given cat seeing a potato. Right. So this is all there is to it in Word2Vec. Given a context, you want to maximize this probability. So there are two ways to implement Word2Vec. One is continuous bag of words, and another is skipgram. But usually people just refer to skip. When people say Word2Vec, they usually mean skipgram. Yeah, they don't use SIBO anymore. I mean, nobody uses Word2Vec. Not nobody, but people rarely use Word2Vec anymore. And even if they use Word2Vec, it's usually skipgram, not SIBO. So the difference between the two is, we'll talk about skipgram first. So what skipgram does is, given a word cat, you're trying to predict the word in its neighbor. So for example, if there's like a boy likes, not likes, not a good example. I'm sorry. A small cat meows shyly. Something like that. Is it the right? I'm not sure if this is the correct spelling, but we'll just move on. Anyway, so if this is your sentence, then and your cat is the main character now, and and small are your context. So what skipgram does is, given a cat, you're trying to predict small, predict A, predict meows, predict shyly. That's it. So given cat, you're trying to given cat, P, A given, not A, I'm sorry. Small given cat, P meows given cat, P shyly given cat. This is it. You're just trying to maximize this probability, and this probability is represented as a softmax function. So that's it. That's skipgram. Continuous bag of words is different. So what they do is it's the same things, but so let's say this is a small cat meows shyly, and what SIBO does is it just adds the word vectors of a small meows. There's word vector for A, word vector for small. You take all them and you sum them up, and then given the sum, you're trying to predict cat. So it's P of cat given sum. So it's the other way around. Skipgram is given a main character, you're trying to predict its neighbor. SIBO is given a context or given a neighbor, you're trying to predict the main character. So it's different. It's like on the opposite way. And in reality, skipgram captures the semantic meaning of words better than SIBO. So all those like, the minus operation, minus plus operation, skipgram shows better performance for that compared to SIBO. All right, moving on. So the size of your context is again a hyperparameter. Like how this could be your context, or this could be your context, or this could be your context. It's all depend on your. They all depend on your choice. So it's a hyperparameter. Like if you want to use size 3, if you when you use skipgram, you use the term skip window, or it's just context window for that matter. So you can set the size of your context window to 3, 4, 5, or 1, even 1. So that if you set this to 1, then this will be your context. If you set this to 2, then this will be your context. If you set this to 3, then this will be your context. Yeah, again, so yeah, the difference between the two. So skipgram is better at semantic tasks, but slow in training. That's because you have to make 5 different, you have to make a lot of more number of predictions. Given a size 2 context window, you need to make 4 predictions, right here. But when you do SIBO, you just make a single prediction. So obviously, skipgram is slower than SIBO. SIBO, it's said that SIBO is good at syntactic tasks. I'm not really sure what syntactic tasks are, but it has its pros and cons. But people usually, almost all the time, they use skipgram. All right, so how word-to-vec algorithm works. So it's just simply, as I said, it's just a softmax, and that's it. So the first loop is your context window sliding over your sentence. So I'm gonna come up with a sentence. There is a dog and a cat. Dot, period. And let's say that your context window size is 1, just for the sake of argument. It's just 1. So in the first time step, you work with this. In that case, is your main character, and there and all is your context. So what you do is you take, if you're doing skipgram, then you try to maximize there given is and P A given is, and that's it. And then next time you move on to the next context, which is this. This is your time step 2. Now A is your main character. Is and dog is your context. So in that case, you can come up with P given is and P given dog. You try to maximize this probability. And this probability here, is representative softmax, but there's something more. There's something more. So now, as I said, so that's what the first loop is for. It's for the sliding context window, like here, 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 and here. You're sliding across a sentence. And the inner loop is where you come up with this, a set of softmax functions. So if your context window is size 1, then you come up with 2 terms. If your context window size is 2, then obviously you come up with 4 terms, 4 probability terms. If your context window size is 3, then you come up with 6 probability terms, and that's it. So, and as I said, individual conditional probability is given as a softmax, or actually a log of softmax. There's a log term here, so it's a log of softmax. Pretty straightforward, right? Very, very easy. So here, this is your main character. This is all skipgram. This is your main character. This is your context. So this is your main character. For example, this is your is, and this is there. Then a vector representation of there. So their vector is plugged in here, and is vector is plugged in here, right? So it's because everything is vector, everything is word embedding. So there should be there's a there embedding, and then there's a is embedding, and you plug them in, and basically you do a inner product between the two. And of course, obviously this is a softmax, so there should be a normalization term here. So it's that you need to calculate the inner product between all pairs of is and all the other like from A to Z, from A to Z. So this is you're looping over the entire dictionary or entire vocabulary, and this actually takes a lot of time. This takes a lot of time, so that's why skipgram is not is a pretty slow algorithm. And note that go ahead. Yeah, note that there are two parameter set two embeddings. I should say two embeddings that you need to learn, because when, for example, I'm going to erase all this. Oh, excuse me. So this is your context window now, and this is your center word. Then, as I said, everything is represented as vector, but the vector for the center word or the main character or target word is different from the vector for the context word. They use different parameters. So here, this is actually a nice depiction. Actually, we'll just forget about it because it's easier to describe this in words. So there are two scenarios. When is a main character, and when is a context. It's a neighbor. There are two scenarios for all words in Word2Vec, and and the model uses two different parameters for two different scenarios. So there's a word vector for when the word is a main character. So in this case, that's why there's U and V here, because there are two word vectors. Like V is for when the given word is a main character, and U is for when the given word is a context. So you use two sets of word embeddings. And some people might say, why use two sets of embeddings? Why not use the same embedding for when the word is both context and a main character? And I guess that also makes sense. People do use that approach sometimes, but I think originally the author of Word2Vec thought that when a word is a main character and when a word is a context, a neighbor, they should serve different roles. They should capture different semantic meanings. So that's why they use the two different word embeddings. But I think it still makes sense to use the same word embedding for two different scenarios. I hope that makes sense. So that's what this page is for. So there's W1 and there's W2. So W1 is for input vector being the main character. So this is for when the words are main character or target word. Some people say the target or the center word. And this is for the when word is the context. And obviously they will capture a bit of different semantics. So when a word, for example, when apple is used as a main character or target word, when apple is used as context, the contents of the input vector. So this is a five-dimensional vector. Their values are a bit different. Even if it's the same apple vector, W1, W, so the first embedding and the second embedding, they slightly differ. And you can see that when eat vector, when eat is the target vector, its content is very similar to when apple is the output vector or the context vector. Like here, this one and this one, they're pretty similar. Like here and here, the contents are pretty similar. Same for this one and this one. It's because it is very likely to see in the same context eat an apple or eat an orange or eat a rice. So they capture similar meaning. But eat and water are not very similar. That's because you don't eat water, you drink water, right? So you can see that drink, and water are similar here. All right. So, all right, question. 네, 맞습니다. 둘 다 이제 컨텍스트가 주어지는데, 그거를 이제 더해가지고, 컨텍스트를 만드는 방법이 그냥 그 주변 컨텍스트 워드를 다 더해가지고 썸을 해버리는 것보다는 그냥 하나하나씩 그 예측을 하도록 강요하는 게 더 이제 그 서틀한 세만틱을 더 잘 캡처한다고 보시면 될 것 같습니다. 네, 하지만 둘 다 컨텍스트랑 타겟을 다 보는 것은 맞습니다. Right, as I said, so softmax tree implementation are very slow. That's because there's the vocabulary size of English is like millions is a bit of an exaggeration, but easily over dozens of thousands. And you have the normalized softmax in the term here. So I'm just going to erase everything. So here, this term actually slows the entire training process down. So people come up with two solutions. One is hierarchical softmax, another is negative sampling. And hierarchical softmax, I don't think anybody uses this these days, but it was proposed in the original paper. And basically it's just, you come up with a binary tree of words. So if you have binary tree of words, then the depth of the tree grows in a log scale compared to the size of your vocabulary, and then you can pre-calculate the likelihood of word probabilities. So, and then you can look it up. But it's a pretty complicated process, so nobody really uses this. So people just simply use negative sampling, which is still used in a lot of tasks these days. Negative sampling. Like contrastive learning, they use negative sampling basically. Anyway, so what negative sampling does is instead of normalizing your softmax function, your P of context given target, we're still talking about skipgram. So instead of, and this is log of normalization term over exp of word vector of UC and VT. Instead of using the full normalization term, they simply sample a fixed number of fixed number of words that is basically not this. So some words, some sampled words, as long as it's not the context word, then you can sample them to a fixed number of times. Like you sample 10 words that are not this word, or you sample 20 words that are not this word, something like this. And then you use that to instead of using the full normalization term, you just use that as a normalization factor. So here, this term is this term, and this term is this term. I mean, I guess this term. And you sample negative, like this is called negative sampling because you sample words that are not the context words. So you sample from the entire dictionary, maybe 10, maybe 5. It's all up to you. It's a hyperparameter. Anyway, yeah, that's it. So you sample, let's say 5 negative words, and then you simply calculate this 5 times with 5 negative context words, and that's it. So it makes the entire thing really extremely faster. Yeah. I mean, obviously, the more samples that you draw, like if you set the hyperparameter to like 100 or 1,000, then it'll be almost as close, almost like similar to this true value, but then you're trading off like accuracy with your time. So it's, yeah, I think people use 5 or 10 and just go on with it basically. Basically, yeah. So yeah, application word to vec. So it's once you've learned the word embeddings, then where you're going to use it. Like since a word already captures the semantics pretty well, where are you going to use it? Then people, I mean, people try to use word to vec embeddings. Like you initialize your word embeddings with the word to vec, and then you try to plug it into different applications like machine translation or semantic analysis, clustering, so a lot of different applications. But it didn't work all the time. Obviously it'll be good for semantic analysis, but I'm not sure if it helped neural machine translation a lot. I'm not sure if that helped a lot, but it's better than nothing though. So, yeah, so that's why people weren't very satisfied with people weren't very satisfied with pre-training word embeddings word to vec and then plugging them in the downstream test because the performance wasn't that great. I mean, still, it was better than nothing, but it wasn't as dramatic as people expected them to be. So that's why people came up with Elmo and BERT, actually. All right, moving on. So, Glove is another word embedding model, and you can think of this as like a globalized version of word to vec, and the title says so, like global vectors of word representation. So what you do is you build a term document matrix. So this is term, this is document. So this is like apple, dog, boy, cat, like different words all here and different. And then this is a count vector, obviously. This is a count vector. And then you use this to learn the word embedding. So you're using this term document frequency matrix. So you're already seeing the entire corpus. In the word to vec, you are sliding your context window over sentences. So it's a very local model. But here you're using the entire term document matrix. So it's a global model, actually. So it's basically I'm sorry. This is not term document matrix. I'm sorry. Sorry about that. This is a co-occurrence matrix. So it's both axes are words. It's the same apple, boy, cat, and so it's just that how many times the words occur in the same context or same document or same sentence, whatever. The unit is all up to you. But I guess it could be a context, like size 5 context window, something like this. So you pre-calculate the occurrence probability or occurrence count. Both are the same thing. So like this could be like 5 times. Apple. Actually, A and apple occurs 10 times, and A and boy occurs 100 times, something like this. So it's a co-occurrence matrix. And then this is a global information compared to just sliding your context window. You have the global statistics of co-occurrence probability. And then you just take that entire matrix and then you calculate. So Pij is a single cell here, like boy and cat, maybe a boy and cat, or cat and boy, cat and boy here. So Pij is a single cell, and then Ui and Vj is the word embedding of the ith word and the jth word in your vocabulary. And Pij again is it's a probability. So they're all occurrence probabilities. So it's a single cell. And F is some function that tries to capture the global like statistics, global statistics. Okay. Right. So you're trying to maximize this term. And by doing so, you're learning these vector representations. So it's way faster. Glove is way faster than word to vec. And it's said that people say that it works well even with a small corpus, but I guess I'm not sure how often people use glove these days. Yeah. Right, moving on. So doc2vec. Yeah, doc2vec is a straight up extension of word to vec. So it's you can also call this paragraph to vec, because it's basically how much you want to extend your word to vec is all up to you. Like if you want to represent a document, that's fine. If you want to represent an article, that's fine. If you want to represent a paragraph, that's also fine. You just need to have a separate identifier or separate embedding for whatever you want to embed. So I'm gonna just I'm going to assume that we're doing doc2vec. So if you want to do doc2vec, you not only prepare embeddings or vectors for your words, but you also prepare embeddings or vectors for documents. So if you have like 1,000 documents and 10,000 words, 1,000 docs, 10,000 words, then you need to prepare 11,000 vocabulary or 11,000 embeddings, because you want to learn the embeddings for documents as well as a separate embedding. So what you do is basically there's a document embedding or document ID or paragraph ID. So there's a corresponding vector. You just do the same. You just do the same skipgram type of thing. You can either do this or do this basically. But if we're doing skipgram, then you given a document embedding, you need to be able to predict the words that occur in your document. It's the same thing. Now it's just that the now document is the target. It replaces the target word role. Like just like you slide a window and you pick a target word and then you try to predict the words around it based on the target word. You pick a document embedding and then you try to predict the words that occur in the document. So that's it. That's basically what doc2vec is. And then once you've done that, then you've learned the document embeddings, and similar documents, content-wise, they should have similar embeddings. Yeah, but these days, people don't do this anymore. People just use BERT and then take the CLS embedding, and that's it. So times have changed. Right, moving on. So yeah, embedding subword encoding. Actually, we don't have a lot of time, unfortunately. So we have 15 minutes to go. Right. So any questions so far regarding Word2Vec? I mean, it's nice to understand. I mean, you'll be implementing Word2Vec in this Thursday. So, but again, it's super simple. So hope there's not a lot of trouble. And as I said, practically nobody uses Word2Vec these days. Everybody just uses BERT. So, but it's still important to know where BERT came from and what Word2Vec, what word embedding is. And Word2Vec, it was such a landmark paper that actually sparked modern deep learning NLP. I guess it's about the same time people came up with neural machine translation, like sequence to sequence or encoder decoder architecture. About the same time. No, this came a bit earlier than that. So this came up in 2013. So it kind of like sparked the modern deep learning NLP. Yeah. So it's such an important paper. All right, moving on to subword embedding or subword encoding. So words in writing system. So I think people came up with byte pair encoding. I think Google people came up with it by audio speech recognition, audio recognition team. Not really sure. People might correct me if I'm wrong, but I think Google's speech recognition team came up with the idea of byte pair encoding. Not really sure. If I'm wrong, please correct me. But basically, the reason for coming up with byte pair encoding, subword, word piece or sentence piece, they're all the same thing. It's just you're done with dealing with words. You deal with subwords. So subwords meaning you want to break up words into like subunits. For example, prepare. Maybe you want to break this into pre and pair. Something like this. Or what else? Dog. I'm not sure how you would break this into subunits, because dog is like it's its own thing. But like preposition, you might want to break this down into pre. Not this one. You might want to break this down to pre, pause, posy, TIHO, like 3 parts. If you know like the Latin and Greek roots of words, then this might seem reasonable. And but you don't want to do this in a rule-based manner. You want to do this in a data-driven manner, because you don't know all the. So again, back to the motivation of why using subword encoding, subword embedding is because companies like Google, they deal with like a lot of languages in the world, basically all languages in the world, like hundreds or maybe 200 different languages. And they don't want to, and if some deep learning or NLP model is based on words, then it's not going to work on all languages, because some languages don't, it's not word based, because some languages don't have like, spacing between words. Like Korean didn't used to have spacing, 띄어쓰기. They didn't used to have that. And like Japanese and Chinese, they still don't have any spacing. It's all like, just sequence of symbols all the way. So it's really hard for people like, it's really hard for people to come up with a proper spacing and treating them as words. So it's easier if you just use a language agnostic approach to encode stuff, right? So if you use words as a atomic level of NLP, then that's not going to do well in languages like Chinese and Japanese and Korean. So you want to come up with a way to treat language, or come up with different atomic unit for language processing other than words. So that's where subwords come in. 서버드 형태소 같은 걸 말씀하시는 건가요? 뭐 우리나라로 치면 형태소입니다. 근데 이게 항상 형태소는 아니에요. And as I said, like breaking preposition down into 3 parts, this is sensible for English, but in order to do this, then you need to understand English, where English came from. Like it's like archaic root, Greek root, Latin root, like Germanic root, and like French root. You need to know all these stuff to come up with like a sensible breaking down. And you don't want to do this for all languages in the world. So you want to do this in a data-driven way, or statistic way, and that's where byte pair encoding comes in. Right, and even if you're dealing with word-based languages like English, still it's not going to work very well, because people often twist or distort language like this, like good vibes, like good. This is not a correct way to spell good, right? But people do this often, and like this, like IDC, like I don't care. I'm going to summon something for you. Like people twist, or like language evolves over time. Nothing is fixed. Like everything changes in time. And in order to do that, rules might change too. So in order to catch up with this kind of like evolution, depending on like data-driven manner is way more sensible than coming up with like elaborate rules. Right, so that's where Subword. So before Subword, people actually tried to use character level NLP. So like basically all Latin-based languages like Russian, German, Italian, Spanish, whatever, like all those like Latin-based Latin-rooted word languages, you can break them down into characters, and this used to be a pretty nice idea, because there are only so many characters in English. Basically, if you're thinking about ASCII codes, and there's like only 50 something. Like there's uppercase characters, there's lowercase characters, and there's like some symbols like question marks and exclamation marks, and then there's numbers, and that's it. So basically like 100 different ASCII codes, and that's it. So instead of having tens of thousands of words, you're only left with like only few dozens of characters, and you can still process all the words, all the documents, all the articles. But the problem is that if you break everything down into character level, then your sequence becomes humongously large, because like a boy is running. If you do this in a word-based manner, there's only 4 words. But if you do this in a character manner, then there's like 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13. It's like there's 13 words. Now your sequence length has like tripled. And if either you're using transformer or RNN or whatever, having a too long sequences is always not a good idea. So yeah, character level NMT used to be a thing back in like 2016, 17, even 18, I think. And it showed promising results even back in 2016. And even outperformed outperformed word-based model, like word-based word-based machine translation 15.7, character-based machine translation 15.9. So it was either better or at least like the same performance. But you can see that 600 step backprop. So that means your input is like 600 sequence length because you're breaking every sentence down into character levels. So it's going to take a long time to train your model. 3 weeks to train, not a good idea. I'm going to just skip over the technical detail. Right. So there's when byte pair encoding comes in. So byte pair encoding is it used to be a compression algorithm. So you want to compress a stream of signals, a stream of codes, basically, when you're like sending signals over, like secret messages, or maybe some byte sequences. Like if you're like a network operator, if you're like an internet service provider, then you're sending sequence of bytes all the time, and you want to make your communication more efficient by compressing your messages or your stream of bytes or stream of bits into like a compact form. So that's where byte pair encoding comes in. So it used to be a compression algorithm, but again, you can use it for NLP purposes. So what you do is a most frequent byte pair becomes a new byte. So replacing bytes with character engrams is basically it. So original compression algorithm is you compress a most frequent byte into a new byte, and then that becomes, for example, let's say 10. I'm just going to use a bit example, 1010111101, and there's like 1010010110, 10101111, something like this. Let's say that there are like 3 different messages. This is message 1, this is message 2, and this is message 3, right? And you can see that 1010 is always there, right? So then it might be a good idea to actually just transform them into different stuff, different encoding. I mean, here it's just that everything is just binary. Everything is just either 0 or 1. But if you have like more space or more room to reserve a encoding, then you can represent them as like a single, like A, like you can all replace them with A. So now it becomes A1111, A11101, A01010. Now you've basically compressed, like you're saving like 3 spaces, something like. Basically, this is like the philosophy of compression algorithm. And simply what you do is you just replace bytes with character. So you can treat your characters as bytes and apply the same byte pair encoding algorithm, right? No, actually, no, I'm sorry. Byte pair encoding was formally first introduced by Senrich. Yeah, I'm sorry. Forget about what I said about the Google people. So maybe they're from Google. I'm not really sure where they're from, but at least like this guy came up with, or woman. I'm not really sure. Rico sounds like a man's name. Anyway, so yeah, Senrich came up with byte pair encoding, and then it was introduced in ACL 2016. So yeah, byte pair encoding. It's a bottom-up clustering, basically bottom-up clustering. Actually, there's a very nice example of how you do it. Actually, it's a very simple algorithm, works very well. So word segmentation algorithm. So you start with characters. So given some language or given some set of documents or some corpus, you start with a vocabulary or dictionary which consists of only characters. So only characters, and then you start, but you go through a for loop where you go through for loop to count the number of things that happen, and you come up with 2 grams, bigrams, trigrams, and 4grams and 5grams iteratively. So most frequent n-gram pairs become a new n-gram. So let's see. So let's say, for example, that in your entire documents, low the word low occurred 5 times. Lower occurred 2 times. Newest occurred 6 times. Wildest occurred 3 times. And given this document, you are given your vocabulary consists of characters only. So there's L, O, W, E, R, N, S, T, D, I, right? So there's characters here, L, O, W, E, R, N, whatever, right? So you start, this is your baseline. This is your first starting point. And then you do a for loop where you go with, so you look at LO, you look at OW, LO, OW, WE, ER, NE, EW, WE, ES, ST, WI, ID, DE, ES, ST. So you take a look at all the bigrams, all the 2 grams in your dictionary, in your document set, and then calculate how many times each bigram occurs in your entire documents. And it happens such that ES happens 9 times because you know that ES is the common bigram in both newest and widest, and newest occurs 6 times, widest occurs 3 times. So ES occurs 9 times in total compared to LO. LO occurs 7 times, 5 plus 2. So this time you select ES to be your new unit. So you add ES to your vocabulary. Right. So that's how you do it. And the next time you take EST. So ES, you can take EST because ES is now a single unit of encoding. It's a single code. So now you can start with you can test things out with LES, OES, WES, EES, RES, NES, WS, something like this, basically, something like this. But that, I'm sorry, not exactly this, actually, not exactly this. So you do the same thing. You take LO, OW, LO, OW, WER, NEEW, WES. Now it's WES because ES is now its own thing. So it's either WES and EST, YI, ID, DES, and EST. And it just so happens that EST happens 9 times again. So compared to like LO, or OW, which are all 7 times, EST happens 9 times. So you register EST as a single unit to your vocabulary again. And what happens to overlapping n-grams with the same or similar frequencies? I think this already answers your question, right? Oh, same. If they're same frequency, then you just register them sequentially. Yeah. It doesn't. Yeah. Overall, if you do this a lot of times, it's just doesn't really matter which one you take first. If certain like n-grams occur the same time, same number of times. Yeah, or like if there was a word like less and less was like 6 times, then it's still like L, E, S, and S. And then you do LES and ESS. Yeah, they're just accumulating the vocabulary. All right, moving on. So next time, now you have came up with ES and EST. Next time, now you can deal with LO. And LO occurs 7 times. I mean, OW also occurs 7 times, but doesn't really matter. You can start with anything. So you're going to register LO to your vocabulary. And then you do this again. Actually, you can do this until even lower, newest, widest, which occurs 5 times, 2 times, 6 times, 3 times. You can do this like, until every single word in your document is registered in your vocabulary. You can repeat this process, obviously, right? Because there's nothing stopping you from actually running this algorithm forever and ever until every single word in your entire corpus is registered in your vocabulary, right? Oh, we is 8 times. We is 8 times. I'm not really sure if you can do this because ES is already like concatenated into a single thing, so you can't do that. I don't think so. So it's a greedy algorithm actually. Right. So as I said, you can go again until every single word is in your vocabulary. And so that's why you need to set a stopping criteria. You don't want, I mean, the whole purpose of having a byte pair encoding or any subword encoding is to downsize the size of your dictionary. You don't want to deal with every single weird word you don't want to deal with like good in your diction in your vocabulary. You don't want to have that. So the whole purpose of the byte pair encoding is actually twofold. You want to be language agnostic, and you don't want to deal with every single weird word in your documents. So what you do is you just simply set a target vocabulary size. Like you just grow your vocabulary until, like, I don't know, when the size is like 30,000 or 10,000, 20,000, it's all up to you. I think people usually use number smaller than 50,000. So people use like 50,000 or 30,000 vocabulary size, and you just run that byte pair encoding algorithm until your vocabulary size reaches 30,000, and that's it. And do deterministic longest piece segmentation of words. So longest piece segmentation. So once you have the word, once you have a fixed vocabulary, once you've run your BPE algorithm and you came up with the fixed vocabulary, then you just when you run that at the test time, you break your words into the longest piece first. So, for example, if you're given like this vocabulary, and given a new word like newest, you take EST first out because EST is the longest one. So because it's a 3 gram, so you take EST out, and then you have what do you have? Then you just have N, E, W, EST. That's how you tokenize your word at test time given a byte pair encoding vocabulary. So it's a deterministic approach, and it's a greedy approach. So it's not really the best way to tokenize words, actually. So people come up with like stochastic approaches, like probabilistic approaches. Like there's something called BPE dropout to kind of like cope with this kind of shortcoming. Yes, and segmentation is only within words identified by some so this is all word-based encoding method. This is byte pair encoding, and this is all word-based. So first of all, you need to tokenize your documents into words so that you can calculate word frequencies first, and then you come up with byte pair encoding vocabulary. So, but as I said, Chinese, Japanese, English, and Korean, they don't have like a clear like spacing or word spacing in their language. So that's when people use like something called sentence piece and stuff. But that's another thing. Yeah, anyway, so this is good because it automatically decides the vocabulary for you. So it's such a nice data-driven way to come up with vocabulary. Given a bunch of documents that you want to model or you want to process, you just run BPE algorithm on that documents, and then you come up with a nice fixed size vocabulary, and then that's it. Right. Yeah, so there's I'm sorry about running a bit. Yeah, I think we have only like 5 more minutes to go. So yeah, and compared to BP, there's something called word piece or sentence piece model, which is developed by Google people, but the philosophy is exactly the same. I mean, the only difference between a word piece and byte pair encoding is how they choose the byte new engram. Like here in BPE, you chose whatever has the highest occurrence frequency, basically. Like if EST 9 times, like here you chose ES because it occurred 9 times. It was the most frequent engram. It was the most frequent bigram. So you chose ES, and then you move on. And you chose EST because it was the most frequent bigram again. So you just BPE selects new entry to the vocabulary based on simply based on frequency, and that's it. But here in word piece, they choose a new entry to the vocabulary, which maximizes the likelihood of your documents. And likelihood meaning just language, like language modeling or something like that. So here, rather than character n-gram count, use a greedy approximation to maximizing language model likelihood to choose the pieces. So you have some language model, and then there's like each iteration, you have a bunch of different candidates to register to your vocabulary, right? And you choose a new entry, whichever maximizes your language model likelihood. So you try out with ES and then see if it maximizes the language model likelihood. You try out with EST, you try out with LO, you try out with OW, something like that. So it takes a bit more time than byte pair encoding. So yeah, so essentially what it does, it adds n-gram that maximally reduces perplexity. So language model likelihood is it's the same thing as perplexity actually. So basically you just evaluate language model with different candidates, and then whichever maximizes language model the log likelihood, that goes into the vocabulary. So that's the only difference between byte pair encoding and word piece. Sentence piece is this is specifically for CJK, which is Korean, Japanese, and Korean. I mean Chinese, Japanese, and Korean. So sentence piece, it retains white space as a special token. So it doesn't tokenize documents into words first in order to apply this algorithm. Like word piece and BPE, you need to tokenize your sentences or documents into words so that you can count words and then come up with new n-grams. But sentence piece doesn't do that. It just treats white space as a special token, which is an underscore, and then you just apply the same algorithm again. You just apply the word piece algorithm on top of this new representation of documents. And good thing about it is you can actually exactly reverse the things at the end by joining pieces and record. So basically, once you've represent. So a boy has a ball. Once then you have this sentence, and you can break this down into Subword encodings. For example, you can break this down into if you're using byte pair encoding. Let's just say you can break this down to a boy has a BA. There should be, I'm sorry. A boy has a BA and LL and dot. Let's say this is BP or this is your word piece. Your sentence piece would look like a boy has, actually there's a special like underscore in front of it because it means there's a space. There's a sharp here. Sharp in BP or word piece means that it's not it's like the intermediate. There's some word in front of LL. So the sharp LL. And a boy has a ball. Oh, so this is how a sentence piece would tokenize this sentence. So the good thing about sentence piece is that you can exactly reconstruct the original sentence given a sentence piece encoding, but you can't do that with BP or or word piece because you don't know where the space was before. Like it just might be the case like there were two spaces between boy and has. Like nobody really knows, right? So given the good thing about sentence piece is that you can exactly reconstruct the original sentence given a sentence piece encoding of a sentence. Yeah, so it's especially useful for languages like Chinese, Japanese, and Korean. And that's it. Right. BERT. Yeah, we're going to get to this when we talk about BERT. But BERT uses a variant of word piece model. So it doesn't completely rely on word piece. It's a hybrid. So it takes some words as words. It doesn't break words. It's basically a hybrid of word-based and word piece model-based. So some common words are in the vocabulary, like even 1910s. Like this is number, but this is registered as a unique, like its own word in BERT vocabulary. But then something like Hypatia, I'm not sure, Hypatia, this is like a Greek philosopher, I think. You can break it down into H sharp sharp YP sharp sharp ATI sharp sharp A. Yeah, using word piece. So yeah, that's how BERT does it. So yeah, if you're using BERT, then you might want to first encode your documents in the same way as BERT does, because you need to have the same set of vocabularies as BERT in order to use BERT. Anyway, yeah. Oh, we have just one more thing. So yeah, just the one last thing. So something called contextualized word embedding. So word2vec, word2vec is also contextual. It's a context-based word embedding, but the value of the word embedding in word2vec is fixed. Once you've learned once you've trained word2vec, then the word embeddings have a fixed value. But in reality, the meaning of word changes given its context. It depends on the context. So for example, here, Elmo is actually like one of the very first contextualized word embedding model. So it's a name of a model. So so as a user, we're asking Elmo, what is the embedding of the word stick? Like I want to have a embedding of stick, which is like some high dimensional vector with some continuous value, like -1, 2.5, something like this. So I want to retrieve a word embedding for stick. And if we were talking about word2vec, then there's only one word embedding for stick. But if you're using Elmo or even BERT or Albert or whatever, if you're using those kind of things, then it's going to ask you how there are multiple possible embeddings. So use it in a sentence, because stick can have multiple different meanings depending on the context. So the user says, okay, I'm going to use it in a way that like this, like let's stick to improvisation in this skit, because stick can have different. It could be like a 막대기, like a rod, but or like when you stick is like you're attaching to something, like stick to, right? So this is the second one, sticking to improvisation in this skit. So we're gonna we're gonna stick to, we're gonna use the improvisation, whatever, like so in that case, given a sentence like this, then the embedding for stick is this. But if we had used different input, like I picked up a stick from the ground or something like that, then the stick embedding would have been different value, like some other value. So obviously this is a way better approach than just word2vec, because exactly as Elmo says, the meaning of a word changes depending on the context, how it's used in a sentence. So that's where like Elmo and BERT comes in. So there are a lot of different things. Like there's BERT, there's OpenAI, there's GPT, there's Elmo. Not sure if GPT is it's a contextualized word embedding approach. GPT is more like a generative model. You can generate sentences, but anyway. So yeah. Anyway, so yeah, these days, like all these variants are a way better approach than word2vec. Is exactly because of this motivated example. So we'll get to that. We'll get to maybe 3 or 4 sessions later. All right, yeah. So this is the end. So in the practice session, you guys will be implementing word2vec, and I'm not sure. I don't think actually running BP is a good example, but you'll deal with byte pair encoding. You'll deal with word piece encoded language, like English in Word, like it's been already encoded in the word piece. So you'll get to test them out in the practice session. All right, so yeah, this is the end of today's class. If there are any questions. No question. Yeah, yes, this is not a very complicated concept. Hopefully it's not a complicated concept. So, all right, if there are no more questions, yeah, then I'll see you this Thursday. All right, thank you very much. 버트에서 스틱은 정말 다양한 인베딩이 있죠. 왜냐면은, 여기, 뭐, let's stick to 어쩌고 할 때, 여기 스틱이 쭉 올라가서 여기까지 나오면, 이게 이제 스틱의 인베딩이라고 생각을 하는 거거든요, 사람들이. 근데 그럼 이제 엄청 섞이고 나니까, 이제 얘가 컨텍스트에 섞이고 나가지고, 이제 이 컨텍스트 내에서의 스틱 인베딩인 거죠. 물론 뭐 이제 기본적인 스틱의 인베딩이 뭐 있을 수도 있지만 이거가 이제 스틱의 인베딩이라고 볼 수도 있지만 일단 버트를 사용하는 방법이 이걸 갖다 쓰는 게 아니라 이걸 갖다 쓰는 거기 때문에 그래서 이제 그걸 Contextualized 인베딩을 부르는 겁니다. 네. 네, 알겠습니다. 예, alright. 우리 쪽에 하나 더 나오고. 그거는 이제 근데 이제 그거는 캣의 인베딩이 이렇게 있어도 거기에 단어를 살짝 뭐 0.1을 더하건 빼건 상관이 없다는 의미에서 이제 그걸 말씀드린 건데 사실은 이제 그 보캐뷸러리에 이미 캣도 막 있으면은 캣을 가져와라. 그러면 이제 캣에 대한 인베딩은 이미 있어요. 워드투백에서 학습이 끝나고 나서. 이제 그거가 1대1 대응이 되는데 거기에다가 뭐 0.1을 더하건 빼건 큰 차이는 없다. 그런 의미였습니다. 네, 버트 GPT 엘모는 다음에 나중에 나옵니다. 네. 버트 엘모는 서버드 인코딩에 서버드 인코딩은 버트랑 상관이 없습니다. 이제 이거는 서버드 인코딩 여기에 센텐스를 어떻게 넣냐예요. 이걸 센텐스를 워드 베이스로 넣냐, 서버워드 베이스로 넣냐 그 차이인 거지. 버트 자체는 그거랑 무관합니다. 근데 버트가 만들어지기를 워드 피스를 기반으로 만들어지긴 했어요. 근데 이거를 워드 기반으로 만든다고 해서 버트가 안 되는 건 아닙니다. 네. Alright, thank you guys. See you later. Bye bye.